Hi, I'm George Chapman, Associate Director with Energy Solutions, here to welcome you to Session 2A, Policy and Codes Aligning Efficiency and Climate Goals. We've got a really great session planned for you today. We'll be talking a little bit about some research that's directly related to codes and standards, the opportunities for improving the performance of water heating systems, as well as looking at the impacts at scale of transitioning towards more efficient water heating. And really, codes and standards are often based on looking at those at scale impacts, those large market sized impacts, and also developing strategies to help move markets towards being able to achieve those impacts. So before we get started, do have a couple of quick things I wanted to make sure we went over. So first and foremost, thank you to all of the sponsors and ACEEE ally members for their support of the Hot Water Forum and ACEEE. This is one of my absolute favorite conferences. I've been lucky to be on the steering committee for almost 10 years. I love this conference, and I'm so grateful for everybody who supports it, both through financial support as well as bringing great sessions and topics and enthusiasm. So thank you, especially to all the sponsors and allies. I want to encourage everyone to use the chat box. It's on the right-hand side of your screen. You can ask questions of the presenters. So the way it works is the presenters will not be able to answer the questions in the chat, but they will be able to see them, and we can speak to them as part of their presentations. And we'll also have 20 minutes at the end for a Zoom room meeting. And if any questions we don't get to as part of the session, we can always address in the Zoom conversation, and we'll make sure to capture those. So please do just use the chat box for the questions as opposed to additional dialogue, just because it'll help me track the questions for the speakers. If there's too much other stuff in there, we might lose people's questions in sort of the muddle. So please just use it for that purpose. Check out the tabs on the left-hand side of the app. You can do things like networking, visit the sponsor pages. There's a game. So you can win free registration to the 2023 Hot Water Forum, which will be live in Mission Hills, California. So that'll be super exciting. There's a resources section for a list of attendees. And if you can help us in planning future hot water forums by completing the conference evaluation. And if you do so and leave a testimonial, you get a $25 discount off your 2023 hot water forum registration. And you all know you're going to need that because you're going to have such a great time this year. You're going to be dying to come back next year. So please go ahead and do that as well. So the presentations will be available for on-demand viewing to the registered attendees through the Socio platform within a couple of days. They'll remain available for viewing until May. The slides can be found on their page in the program participants section. So in a moment, I'm going to introduce our speakers. But before I do that, we've got a brief message from one of our Hot Water Forum sponsors, A.O. Smith.
To be innovative, you have to think outside the box, which is rather ironic because at A.O. Smith, all our outside-the-box thinking goes, well, right back into a box. For nearly a century, we've been building innovation into a wide range of water heaters that can fit anyone's lifestyle, which means that our outside-the-box thinking goes right inside your home. A.O. Smith. Innovation has a name. To get an A.O. Smith water heater for your home, visit hotwater.com and click where to buy.
Wonderful. So I'm going to introduce our first speaker, Gina Rada, currently the owner of Gable Energy out of Castro Valley, California. She's been doing in the energy modeling field since 1991. I don't believe that. Is the instructor of several dozen full-day Energy Code ACE trainings on the residential and non-residential Title 24 building energy efficiency standards for building department staff, energy consultants, engineers, and architects. She's a Title 24 energy analyst performing a wide range of responsibilities in residential and non-residential construction pertaining to compliance standards and energy modeling. Respected subject matter expert informing statewide code development process. We're fortunate enough today to have Gina sharing perspective on California's 2022 Building Energy Code regarding solar, thermal, and photovoltaic options for residential central domestic hot water systems. So it's really my pleasure to introduce Gina, and I'll let her take it away.
Very much. So I will get jumping right into this since we have so many great speakers who will be speaking after me. And there's a lot of research that's going to come after my presentation. What's pretty exciting about my presentation is this is where all the research is helping develop. And that's when the code hits the ground in terms of taking all the research and applying all of that research into code development. And this is a preview of what's going to be happening on our next code cycle in California that goes into play for projects that go for permit as of January 1st of 2023 next year. In California, we put things in three different buckets when we look at energy compliance. We have mandatory measures, and these are measures that are found to be cost effective all the time, because that's part of the exciting part about California Energy Code is that it's based on cost effectiveness. And mandatory measures are measures to be found cost effective in all of our 16 climate zones. We do check and make sure everything is cost effective in each location in California. And for all scope of work, whether it's new construction, additions, or alterations, which is many times the least expensive time to integrate energy efficiency into a building. Prescriptive measures are measures that show cost effectiveness to maybe only one scope of work, one type of building, or maybe for only specific climate zones. Prescriptive is also a way of showing compliance, but we find a lot of people use our performance approach that we have in California. Performance approach, you use state certified software, which everyone loves, let me tell you, and it allows you to trade prescriptive measures down as far as mandatory minimums, but never lets people trade away those mandatory minimums. My topic I want to talk with you guys today in these buckets of mandatory versus prescriptive and the performance option in California is going to be about central water heating options for our R occupancy buildings, which includes multifamily buildings of any size and the hot water systems associated with hotel motel buildings. I will not be covering single family. So one of the things that we got new to this next code cycle is a new metric that goes on under the hood when we use our performance approach. Up until this time, we looked at energy efficiency measures in the measurement of time-dependent value, TDV measurement. What time is the energy being used, dependent upon where that building is located in those 16 climate zones, and what energy source are they using. New to this next code cycle is a source total metric that's looking at the carbon footprint associated with the specific energy type being used. So that's a whole new thing that we're looking at as we're trying to go to a carbon zero grid, shall we say, here in California sooner than later. When we look at our central water heating options for our multifamily and hotel motel buildings, I am only going to be looking at central systems, and that's where I have one piece of equipment that's serving either multiple dwelling units or multiple hotel motel rooms. I will not be looking at the individual one water heater for every dwelling unit option. I'm going to concentrate on central. So pretty self-explanatory if you want to use gas, and gas still is a choice in California in this next code cycle. You're going to take a penalty for going with a gas central system because of the source energy calculation that's going on under the hood with our performance calculations this next code cycle. You'll have to meet minimum efficiency requirements. That makes sense. Recirculation is something that's very much looked at in California. What can we do to help improve energy efficiency there? And we're going to hear more in just a few minutes about some of the research that went behind what we see in California. If you go with a gas central water heating system, you will have to prescriptively provide a solar thermal system to be paired with that system. What's new is now we are looking at central heat pump water heating systems. And they said heat pump water heating systems don't have a certification requirement or procedure yet through the federal government. So California came up with a efficiency measure that is explained in what we call the Joint Appendices Chapter 14, and we'll talk a little bit more about that. Yet again, there will be recirculation control requirements. And what will be required is that the design system will have to meet design criteria associated with central heat pump water heating systems. What you don't see here is if you go central heat pump water heating, you will not have to do a solar thermal system. But you'll see in a few minutes that PV is going to be required in this next code cycle for these building types, and that's where we're getting the source energy, shall we say, at the site to help support these systems. So there are 4 major components to central heat pump water heating systems. Remember I said it's not an efficiency, we have a design criteria. This is a breakdown of that design criteria of what needs to be in play as meeting these prescriptive central heat pump water heating requirements, which will set baseline in our performance calculation, with the exception with the bypass. The baseline will be single pass, whereas prescriptively you can either do parallel multipass and or single pass. You can decide which way you want to go prescriptively without penalty. It's totally supported either way. But you'll see that there's specific requirements regarding the transfer of water, which is potential loss of energy, between the heat pump systems generating that heat to the primary storage tanks, and then also the compressor cutoff temperature. The primary storage tanks, we really need to make sure that those are sized properly. Undersized storage is the big point of failure that might happen with central heat pump water heating. So we have temperature set point requirements, tank insulation. I hope everyone just realizes that's just kind of common sense, and specific language about the recirculation return loop. Temperature maintenance system is a choice, not a requirement. If chosen, there are specific, I'm talking about recirculation loop tanks, so sorry about that. Temperature maintenance system, that is the piping that's combined with that recirculation loop. That's how we're moving the energy around that hot water throughout that system and throughout the building. And that's where you're definitely going to see the recirculation requirements in terms of pumps, in terms of loops, in terms of pipe insulation come into play, and very specifically controls. Recirculation loop tank, if you want to do auxiliary heating for those systems, that's where it's a choice. Electric resistance is okay, or it could be, which we almost want to see even more, another heat pump water heating system or piece of equipment that will help satisfy that auxiliary heating if needed. All of this then has to be documented at design per the design criteria that I just talked about in our Joint Appendices Chapter 14. This is another document that supports code here in California. It's not the code language itself, but it's appendices information that supports how things are to be installed and designed. So this is how California is trying to set a minimum standard of design efficiency, since we don't have a tested efficiency rating that we can tap into. Again, solar thermal systems are only going to be prescriptively required when I have a central gas system, whether that be natural gas or propane, of which, depending upon your climate zone, in our milder climate zones, is required a 20% solar saving fraction. To me, that's such a low bar to pass. These to me seem very low numbers. Most of the solar thermal systems I see are 55 to 60% solar saving fraction. So there's a lot of room for growth in our systems in providing more stringency than required by the state code. In our hotter climate zones, more stringent temperature fluctuating climate zones, that solar thermal fraction is a 35%. We're trying to introduce drain water heat recovery more into our buildings, and one of the ways that it's used to help support our central water heating systems is that if people want to reduce the prescriptive solar fraction for these gas systems, they can do that by engaging the design and use of a drain water heat recovery system. Part of what I want to talk about is our renewable requirements that are brand new to this code cycle for this particular building type, both hotel, motel, and high-rise multifamily buildings. Those are buildings 4 habitable stories or greater. We're looking at all the roof areas associated with the project, the roof of the building itself, but any other buildings or other structures on the property, such as carports. And the requirement's going to be based on, well, what climate zone are you? And we provide a factor based on climate zone that is multiplied times the conditioned floor area of the building. Or how much roof do you have, viable roof do you have, and multiply that times the number, 14 watts per square foot. Whichever is less is going to set the minimum PVKW requirements of that building. The performance approach may provide flexibility. We don't quite have the software yet for the next code cycle, so I honestly haven't had the opportunity to explore what that might give us in terms of, can we do greater PVKW? Can we do less PVKW? I'm not so sure yet. There are some exceptions to when you don't have to consider PV, you don't have enough solar access. And they've defined that to be you don't have at least 70% annual solar access over the course of an entire year at any roof on the property. We do get to exclude occupied roofs. This is brand new for this code cycle, in which that is an exception. And any roof area that needs to be reserved for other code requirements, such as fire egress or window washing egress. What's also pretty exciting in California, for the very first time, battery storage will be prescriptively required. This is the kind of ground shaking, oh my. And this is associated with our multifamily buildings 4 stories or greater and our hotel motel buildings of any size. It is not associated with our low-rise multifamily buildings, which are 3 habitable stories or less. So there's a little bit of a difference depending upon how many stories associated with a multifamily building. But this is 100% tied to how much PVKW is required. So there are requirements based on climate zone, and it looks then at the PVKW requirements of PV and applies storage and energy factors that are going to dictate the size of the battery. There are some exceptions also to batteries, such as, well, your PV size that you're actually putting in the building is less than 15% than what you were prescriptively required to do. That's a turnaround, easy to understand. Or if you do all of the calculations and it has determined that your PVKWH of the battery is less than 10, that is an exception, since that is an expensive system for a low load. And remember, the energy code is based on cost effectiveness. We at Energy Code ACE are here to help everyone understand the code. We are paid by ratepayers of California. So if you do work in California, or you just want to find out more of what California is doing, come on over to our website, and we have lots of information that we're providing to help our entire organization and people working in California to be up to speed on all of these code requirements starting next year. Thank you.
Well, thank you so much, Gina. That was tremendous. It's really exciting to see all of the interesting work going on to the California building codes. And what really struck me about it personally was just seeing the options and the varieties of opportunities to innovate and design efficient systems in a number of different ways, and with a number of different opportunities to build the system that is appropriate for different building types. But also ensuring that they're high efficient and taking advantage of things like solar, storage, communication capabilities, and drain water heat recovery, all of it sort of integrated in there, all of the different flavors. Really interesting to see where a lot of, as you said, the research and the topics that we talk about at this forum, how they make it into the code and how they ultimately make it into buildings, in this case in California, but often, as we know, can be a model for national codes as well. So that was a tremendous start, and really interesting to see sort of where a lot of this work goes. So next up, we'll have Christian Valoria. Now, he's a building systems engineer at the Pacific Northwest National Lab, leading technology development deployment campaigns with a focus on underutilized energy efficiency technologies. Performs energy modeling for technology assessments. He's got a BS and MS in mechanical engineering. He's a licensed professional engineer, active member of ASHRAE, and he is going to be presenting on some modeling related to heat pump water heaters. And so the way that I like to think about this in this kind of codes perspective is these are the types of large scale impacts that can help drive the code process. and is an integral part of that process. So we'll be very interested to hear from Christian on the modeling and the impacts that he's demonstrated through his work. So please join me in welcoming him to the stage.
All right, well, thank you for that introduction. Like you said, I'm an engineer at the Building Systems Group at PNNL. I've been there for just over a year now, and I will say that this is my first time presenting at the Hot Water Forum. I'm very honored and excited to do so. I will also say that I am just starting to get a cold, starting a couple days ago, actually, so you'll have to bear with me. My voice is a little bit affected by that, and my cognition might be a little affected by it too. Anyway, I will be talking about domestic hot water load decarbonization. And this is not for central water heating systems like Gina talked about. This is for single family homes and those types of applications. So first, I'd like to give a little bit of a background. As many of us here know, our country is shifting toward electrification of residential buildings, and this is a large part of our overall decarbonization strategy. The thought being that we both electrify end uses in homes like cooking, space heating, and water heating, while also decarbonizing the electric grid. Now, in single family residences, however, this becomes particularly expensive when a home needs a panel upgrade to accommodate a 240 volt heat pump water heater. Maybe, where there was an electric resistance storage water heater, the existing panel could be sufficient for that 240 volt heat pump water heater. But when the water heating load was previously fossil fuel fired, it's likely that the panel capacity might become an issue. That, paired with the reality that most water heater replacements are reactionary rather than proactive, make fuel switching a challenging endeavor for any homeowner. Now, the retrofit-ready heat pump water heater specification mobilized the development of plug-in 120-volt heat pump water heaters capable of operating on a 15-amp circuit to accommodate homes without the electrical service and panel capacity for 240-volt heat pump water heaters. We have heard that the 120-volt heat pump water heater does not have an auxiliary heat source and may have performance limitations in larger households in colder climate locations, especially where water heaters are installed in semi or unconditioned spaces. And the other thing is that, because they can plug into a standard residential outlet, it almost gives off the impression that these heat pump water heaters are plug and play, which may be fine for some houses in warmer climates and smaller households. But real thought and effort needs to be put into sizing, siting, and selecting proper features to meet demand, particularly in cold climates and larger households. So what did we do? We did a scoping analysis, a very light scoping analysis to address challenges for electrification of residential water heating loads, particularly to further understand different 120-volt heat pump water heater configurations and where they may be applicable to target residential building stock. We did so in two ways. So the first way, the image over to the right here on the top, we did a 1-hour hot water delivery assessment to assess the delivery capabilities of different heat pump water heater configurations in different locations as compared to the baseline water heating systems. The second thing we did was a simplified hourly analysis. As you can see on the bottom left, this is just a snippet of the Excel spreadsheet. And this was to model energy use, carbon emissions, utility costs across different climate zones, water heater locations, household sizes, and heat pump water heater system configurations. So the first method that we tried, first we wanted to see at a very high level how 1-hour hot water delivery capabilities for 240 and 120-volt heat pump water heaters compared to their prevalent counterparts. So we did so by doing something that's not necessarily a first hour rating. This is a little bit of a different calculation, and the equations can be found on the bottom of the screen here. This is really just to give us a sense of how hot water delivery may change from the prevalent water heating technology in each city. For example, we may presume that the typical type of installation in Rochester, Minnesota would be in a basement, and it would be a gas storage water heater. So if you could see off to the left column here, that's why we have that as 0%. And all the different water heater types and configurations, um, you can kind of see how that 1 hour delivery may change with those different types of configurations. And we did this for Rochester, Minnesota, San Diego, California, for a gas storage heat pump water heater in a garage, and for Seattle, Washington, with a electric resistance storage water heater, also in a garage. So it's worth noting that to accomplish similar hot water delivery capabilities while fuel switching, the amount of storage for the heat pump water heater needs to almost double in most cases. So for Rochester, with the baseline of gas storage 40 gallon, we need to go somewhere around a 240 volt heat pump water heater with an 80 gallon tank, or a 120 volt heat pump water heater with a 80 gallon tank and a mixing valve to meet that same 1 hour delivery capability of that gas storage water heater. So this really just gives us a high level overview of, what the delivery capabilities might be from the prevalent technology. The second thing that we did was we did a little bit more of a detailed hourly analysis methodology. So we did this to really explore the different heat pump water heater configurations and their applicability to different target housing stock. In this parametric analysis, we looked at both 120 volt and 240 volt heat pump water heaters. We used a standard compressor size of 500 watts, but also wanted to investigate how might a larger compressor impact our results. After looking at the slide previously, we thought that there might be an opportunity to increase compressor size just to somewhat match the input that a typical gas water heater might have, or get closer to it, not match it. The other things that we varied were tank size, as well as whether or not the heat pump water heater had an integrated mixing valve. And in total, the parametric analysis resulted in 3,360 runs. You can see all the representative cities that we have here, the different domestic hot water system locations that we've modeled, as well as the different number of bedrooms, 1 through 5. You'll also see the data sources in this table to the left here. Now, a few disclaimers for this model. We did use the very simplified heat pump water heater control logic to determine when electric resistance is triggered. And that's based on number one, the last hour's tank BTU capacity and the entering air conditions. So I can't remember what exactly the threshold was, but if in the last hour, the tank dropped below 10% of total capacity, then we would fully recharge the tank. Or we'd go into electric resistance, 30% in electric resistance. And then also if the entering air conditions were below the compressor cutoff temperature, then we would also be operating in electric resistance. The other thing that we did that I'll have to note is that we did use a simplified model for entering air conditions for unconditioned, semi-conditioned, and conditioned spaces. If you wanted to learn more about that, then I can talk a little bit more about that in the Zoom call. And then another challenge that we ran into was how would the model react to there being a runout event? So for this model, if there was a runout, the tank was recovered to full heating capacity in the next hour. And the other thing that I will also note is that we only used one set of draw profiles. So those are the standard Building America domestic hot water schedules, and I summed them hourly. So we really don't know how these results may change for different types of draw profiles. So these are some sample results that we got. what this is showing is the impact of different heat pump water heater configurations on the modeled number of hot water runouts. In this image, the blue dots represent the represented cities for each climate zone. And I apologize if they're difficult to see, but the white numbers down the middle of America represent the modeled numbers of hot water runouts for each climate zone. For this particular illustration, what was modeled was a 120 volt, 65 gallon heat pump water heater with a 500 watt compressor and no mixing valve, and located in the garage of a 3-bedroom home. So this analysis really helps us understand the relationship between heat pump water heater configurations and their ability to meet demand in different locations, number of bedrooms, and their site. This particular configuration works in a garage without runouts in climate zones 1A, 2A, 2B, 3B, and 3C. It also confirms something that we already do know, is you probably shouldn't install a 120 volt heat pump water heater in a cold garage in Duluth. So this is just another example, playing around with the different variables here. Instead, for this one, we used an 80-gallon tank with a 1,000 watt compressor, and then also with an integrated mixing valve. Now, as you can see, the combination opened up the possibility of potentially installing this particular configuration in the garage of a 3-bedroom home in climate zone 3A, which I believe is Atlanta. You still might experience some hot water runouts, and these numbers I would say are more so for comparison. Like I said, we didn't run this on multiple types of domestic hot water schedules, just the standard schedules from Building America. So that would be somewhere that we could take this a little bit further. So as part of the hourly analysis, we also looked into utility savings and carbon emission savings for our different system configurations. With all the different combinations of features of heat pump water heaters coming to market, it's essential that proper education and design guidance for sizing, selecting, configuring, and siting heat pump water heaters is available to contractors and to do-it-yourself installers. Now, in a case that's shown here, like in San Diego, where many of these different configurations would work, what criteria should a contractor use to select the right configuration? Since carbon emission savings, as you can see in the second to last column, it's almost negligible for these different combinations of technologies and sites or heat pump water heater installation locations. Should the utility bill savings be a priority? Who knows? Well, I would say one big emission from this table is first cost and including installation. And a full life cycle cost analysis could be useful here as well. That way we could see really over the life cycle of these different types of systems and configurations, what would be the most cost effective. And in conclusion, so we saw that the 1-hour delivery capability for heat pump water heaters was typically less than that of gas storage, and tank size nearly had to double to come close to the same amount of 1-hour delivery. In our hourly analysis, we found that the 240 volt heat pump water heaters could meet the demand in most homes, and that different 120 volt heat pump water heater configurations could work in many locations, but great care should be taken for each individual installation, or to create guidance for certain regions for which configurations work. There are also a lot of variables to consider in regards to heat pump water heater selection and fuel switching. So where should the heat pump water heater be located? Is an integrated mixing valve necessary, and what size tank is necessary? And there are also multiple decision points. So number one, is that tank, is that heat pump water heater, is it able to meet the demand? And then also, you would have to decide on, what saves the most money and maybe what reduces carbon emissions the most. So I think this study, this assessment can go a lot deeper. It was very much a scoping study, so there's a lot more to play around with it and explore and fine tune. But I think it really gives us some good insights onto heat pump water heaters. And I think that that's all I have.
Wow. Christian, thank you so much for sharing that. There are a bunch of questions here in the chat. We'll have a chance at a minimum to respond to those for the Zoom, or possibly at the end of this session. I do want to make sure that our last presenters have a chance to provide their information as well. So we'll probably hold off on responding to those right away. But thank you for putting the questions in the chat there. That'll allow Christian to follow up either as part of this or offline as well. Very interesting there to see, I guess, really the start of the conversation, which is where are things going to work? What do we have to be thinking about? And where do we have to be careful about the recommendations that we're making, and making sure we're providing the proper guidance to ensure that consumers are getting the amenity that they need. So that was a tremendous presentation and really appreciated. We'll be transitioning now to our last set of speakers, Pierre del Forge from Nrdc and Deepak from Energy Solutions. So Pierre leads equitable building decarbonization at Nrdc, or the Natural Resources Defense Council, advocates for transformative policies to accelerate the transition of fossil fuels in buildings, the focus on electrification, energy efficiency, and grid flexibility. Deepak is lead economist at Energy Solutions. He's a PhD from the University of Michigan and specializes in energy analysis, modeling, and statistics, an array of stops in energy efficiency, climate, aviation, and data science throughout his career. Deepak has supported PNNL on DOE appliance standards during the Obama administration, and he developed some of the economic and energy models used by DOE in the appliance standards rulemaking. So they've got a tremendous presentation today. Regarding some work that they have wanted to share regarding on-demand domestic hot water recirculation. And so I will pass it along to them to share their presentation.
Thank you, George. And hi, everyone. Thank you for joining our panel. I'm going to try and bring it home and leave enough time for questions. And so I'm sharing the stage here with my colleague Deepak from Energy Solutions, who worked on this study together. And I'm going to take the first few slides, and we'll hand it over to him for the methods and analysis and results. So our presentation is focused on recirculation pumps for hot water, particularly on the opportunity to move to on-demand type of pumps and other advanced hot water recirculation pumps, and also on our thoughts on how to tackle this large decarbonization opportunity that they present. Initially, this started as a California-focused project because it was driven by the California's flexible demand appliance standards rulemaking. But obviously, this work has national implications. Let me see, how do I switch slide here? Let me just find the right button. Okay, great. So as I said, I'm going to give a little bit of background and context and hand it over to Deepak. So hot water recirculation pumps have two major benefits. The first one is convenience, getting hot water faster. No need to wait too long before you get under the shower or wash your hands. And they save water, quite a lot of it turns out, when you add up all the water that otherwise goes down the drain waiting for hot water. However, the vast majority of circulators in use or sold today have a dirty secret. They run 24/7 or are always on, which makes them one of the biggest energy hogs in the homes that use them. And by doing that, they waste both electricity to power the pump 24/7, as much as 2 refrigerators worth, and a lot of thermal energy to reheat the water that cooled down due to excessive recirculation. And we'll see that this is actually the hidden part of the iceberg. And there's also an equity angle to this question, because this energy waste disproportionately impacts renters and people living in large apartment buildings who are more exposed to these pumps than single-family home dwellers. So recirculation pumps can broadly be classified in 3 categories in terms of the controls they use. The first one, obviously, is the one without controls. And unfortunately, that's the vast majority of the pumps that are being in use today and still sold. Then the second category is one notch higher is timer-based recirculation pumps. It's a bit better, but field data shows that a lot of these timers are not effective. Many of them are disabled over time, actually about half of them. And those that remain enabled run the pump for most of the time. So they really don't save that much. And then you have the advanced category, which has a number of different types. The first one, maybe the most obvious or known, is the on-demand type. Although the on-demand type doesn't necessarily work for all applications, particularly in large buildings where other types of solutions like aquastat controlled and thermally balanced variable speed tend to be very effective for this type of applications. All right, with this, I'm going to hand it over to Deepak to take us through the methods, analytics, and results, and I will bring it home with the last couple of slides.
Gotcha. Thank you, Pierre. So this is how we set up the problem. We wanted to find out what happens when you go from a 24/7 continuously operating circulator pump to an on-demand pump. So that's your start point and end point. And then we wanted to find out what are the benefits from it. So there are two types of benefits. The one that is more commonly studied is the electricity savings from reduced pump operation. As you move from a 24/7 case to an on-demand case, your pump is going to operate for a lower period of time throughout the year. So there is that benefit. And then the often less studied one, where the actual thermal the fuel savings from reduced water heater operation as well, because when the circulator pumps operates for a lower period of time, the water heater in itself also operates for a lower period of time. So that is the less studied one. And we also took a first pass at it. The results are approximate in that context in terms of fuel savings, but we did want to take a first pass at it. And then the metrics is essentially energy and CO2 savings. And towards the end, we also calculated payback period to see if it's economically beneficial in this case, or if the investment pays for itself within the lifetime of the circulator pump. Next slide, please. As you can see, the two stars, the star on the far left, that's a 24/7 continuously operating pump. So obviously it operates for 8760 hours a year. And then the far right, So if you shift to an on-demand choice, these estimates are from DOE RFI for circulator pumps for hot water recirculation. So when you go from 8760 to 92 hours, that's where your benefit derives from. That's the reason for the benefit. So we wanted to find out, for ground truth based on DOE RFI's estimates, we wanted to find out how much of benefits we can accrue when we make the shift, and how does it differ based on different water heater type technologies as well. Next slide. And obviously, as you can see, the blue component of these bar plots are the same, because regardless of what water heater you pair a circulator pump with, it's always going to have the same amount of electricity benefits, because the circulator pump operates for a reduced period of time. But then the fuel savings is contingent on whether you pair it with a gas water heater, electric resistance heat pump, or propane. And also, the orange bar here is a function of fuel price. No, not in this case, but essentially it's a function of both the fuel that's used to power the water heater, and then on top of that, you can also look at the electricity benefits. So from our estimates, because we did use deterministic estimates, from our understanding, between 20% and 50% savings is possible when you use an on-demand circulator pump, and when you shift from a 24/7 to an on-demand circulator pump. Next slide. And we also wanted to understand if it's economically beneficial to shift. So if you look at the blue bar, that only takes into account the reduced electricity, or the electricity savings possible from reduced circulator pump operation. So that's the same across all water heaters. And then when you add the fuel savings on top of it, then the system pays back for itself faster. So it's a case of how much you reduce when you shift to an on-demand circulator pumps, and also So, and also what water heater you pair the circulator pump with. So both of them drive the benefits. And in all cases, obviously you see a range of results here, but you can see that in all cases, it's much lower than 15 years, which is the industry standard for an average circulator pump lifetime. And I'll give it back to Pierre.
Thank you, Deepak. So how big of a deal is this opportunity? When you do the numbers, it turns out it's pretty big. So we modeled two scenarios in terms of penetration of various mix of water heaters over the next 10 years based on different California policy scenarios. The first one, the high scenario, is based on AB 3232, which is the law that required the California Energy Commission to assess the feasibility of decarbonizing California's buildings by 40% by 2030 from a 1990 baseline. And then a slightly more modest scenario that sees significant but slower electrification. In both scenarios, the circulator was replaced by an on-demand model at water heater replacement. And the analysis was focused on single-family residential. So we found that somewhere between 5 and 6 million tons of CO2 over 10 years, over the next 10 years, just in California. So extrapolate upward of 50 million tons nationwide. And again, that's just for single family residentials, not including multifamily central systems, which would increase this significantly again. So this makes recirculation pumps one of the major opportunities for building sector decarbonization, and one that is super cost effective. When you look at Deepak's numbers, payback between somewhere between 1.5 to 7 years. So that's one of the most cost effective decarbonization opportunities, and one of the most major ones that's available to us in the next few years. So the last question we want to cover is, what are the policy instruments available to capture this opportunity, particularly to win the big prize, get the entire market and existing building stock to transition to advanced controls? So the four major ones that we identified were the DOE, Department of Energy, Appliance Energy Conservation Standards, which are in progress. The RFI just closed, and we're looking forward to seeing the proposed standards. There's also, California has its own Title 20, which is its own appliance program. And particularly, recently, or last couple of years, the Senate Bill 49 in California gave CEC new authority under Title 20 to set appliance standards for demand flexibility, so basically for controls. So under this particular authority, California could set standards for controls on demand recirculation pumps. And then the other two major approaches are building codes, but for new construction that's already being used, and both under the National Model Code, IECC, and in California with Title 24, where they've already set requirements for new buildings on recirculation pumps. But the big opportunity, if we want to address the existing building stock, basically alterations, would be to require the replacement of the pump at upgrade, or the replacement, or the upgrade, or the retrofit. There are some fairly cost-effective retrofit solution to make a 24/7 pump on demand, and to require that upgrade at time of water heater change out. So the challenge obviously is there's enforcement, but if we need to solve this for other reasons anyway. So when we do, code requirements for alterations could become a mechanism for advancing this opportunity. So there may be others. We welcome other thoughts as part of the discussion on other policy options to tackle this opportunity and this source of energy waste and pollution. Thank you.
Great, thank you. And if we can get the rest of our panelists up here, I appreciate everybody being economical with efficient. They were efficient with their time, giving us an opportunity to have a couple of minutes here to address some of the questions from the audience. So before we did that, Gina, prior to the conversation, you had mentioned having some thoughts or perspective on the recirculating information that Pierre just shared relative to the current California Building Code. I don't know if you had any thoughts you wanted to share there.
Well, Pierre talked about it in that last point about how the building code, and that's how California Energy Code is built into the building code for new construction, single family, and for alterations in which they are replacing the water heater. The only recirc pump control allowed is on demand. which, as Pierre just showed, is the one that has the highest savings associated here in California with any water heater type that's being installed.
Great. So it's good to see some progress on that front and alignment of the research in the code. So that's thank you for sharing that perspective. Christian, there are a couple of questions for you in the chat. The first one I want to make sure is is the report you shared publicly available? I want to read it if nothing else.
It isn't. Like I said, it was just a scoping study. So we don't have any report. It was yeah, unfortunately not.
Okay. Well, then you're going to get a lot of questions in
Yep.
your inbox. You're looking forward to those. I don't know if you had. There are a couple other questions for you here. I don't know if you had any of those answers just off the top of your head regarding the assumed efficiency of the gas water heater, or there was a question about the mixing valves as well.
Yeah, I can run through all these real quick.
Okay.
So the baseline water heater gas efficiency, we use a UEF of 0.62 and a recovery efficiency of 0.78. So the set point question, what set point is used for these cases? So without a mixing valve, we simply modeled it as a set point of 125 degrees. And with a mixing valve, again, simply modeled it as 140 degrees and held it at that. We didn't incorporate any sort of load shifting or anything like that. Yeah, the study results aren't there's no report, unfortunately. Chris asks, does anyone have any information about water heaters installed by region and climate zone? And we kind of did the brute force method where we did all combinations of water heater installations in garages, basements, and closets in all climate zones with basically every single combination that we could. And that's something that we do want to eventually look into is, where are water heaters actually commonly installed in different regions, right? I doubt that there will actually be a water heater installed in a garage in Duluth, but there might be. There might be one somewhere. So, we're just kind of going with our that brute force method. We have one other question: is a hot water runout metric in the P&L analysis on an annual basis? Yes, that is on an annual basis, and I think it's difficult to define a hot water runout as well as what to do. Wait, at least from a modeling sense, what to do in that case. So, and the other thing that I will mention is that this was only based on the standard Building America domestic hot water schedules, and those schedules do have some pretty high draws. At some point, I think January 19th is is the day that I'll remember. So it'd be interesting to run some different other profiles with this model.
In terms of that, there was a question about modeling it up to 160. I guess the question is what are future plans? Do you have future plans for using this model? Looking at scenarios, or what's next there?
Right now, there's not many future plans. We're hoping to eventually get funding to do more of this work later on.
Okay, perfect. Thank you so much. So I really appreciated everybody's presentations and the different topics that we addressed. I don't see any other questions here in the chat. I was curious if there was anything from the other presentations that kind of struck any of the presenters. I can share a couple from my perspective. I'll share one for each, and then if you all have a thought on something that you saw in someone else's presentation that really struck you, I'd be really interested to hear it. So for me, for Gina, is one of the things I really appreciated about what you were sharing and that perspective was just the variety, as I mentioned, the variety, the options, and the different ways of trying to really get at performance, but allow for flexibility, allow for appropriate installation. So I appreciated, really that insight from that presentation. Christian, the thing I took away from yours was the challenge. Really was there. The 120 volt and some of the new technologies are very appealing, but there's a consumer amenity aspect that we have to be very careful about, and making sure that we're thoughtful. And anytime you need to be thoughtful, anytime it isn't just a simple one for one, that means there's education. That means there's information. The kind of work that Gina's doing with Energy Code ACE, she can tell you how hard it can be to make people aware of the code or those considerations or work with those stakeholders. That really struck me. And then lastly, Pierre and Deepak was really interested to, I guess, just the scale of the opportunity and the potential and how much. What I really was interested in was not just the efficiency from the pump, but the efficiency from the system, and really thinking about that. So those were the ones for me, but I don't know if others had takeaways from other. Oh, Gina, please go ahead.
I have to say that when I was listening to Christian's and especially giving us the different impacts of where the systems were located and the different tank sizes, that we as a construction industry have a tendency to not think about the overall impact of the equipment that's being installed, because they walk away, call it done, and that lingering impact of efficiency and also energy bill impact that can make the homeowner potentially be very sad about the investment they made. And that's what I took away from Pierre and Deepak's also, is I wish we could show homeowners more. This is the impact of you saying, I don't want that control. I don't want to hit a switch. I don't want to think ahead of time that I want hot water. I just want it to always be there. And to give them, this is the cost savings on one end, and here is the environmental savings on the other end.
And I had one more point that Pierre actually mentioned briefly. So we just the Federal Reserve just raised interest rates about 1/4 percentage point to curb inflation. National inflation is about 7.9% right now, and a good chunk of it is driven by food and energy prices. So anything to address energy prices will affect the system as a large, but also would go a long way in making life easier to people who belong to the low medium income bracket as well. So definitely has equity considerations, and we shouldn't forget that.
I had a couple of thoughts to share. One on Gina's presentation. I think it was interesting to see how the Energy Commission in California was able to bring in a new technology, because central heat pump water heaters is still a fairly nascent technology, and the market is learning. We're pushing it, and it's coming strong, but it's still very early days. And how the code was able to include this from the start in a way that's flexible to allow for innovation. I think that this is like a chicken and egg, that this technology can't get to market until it's allowed by code, and the code doesn't allow it until there's enough critical mass to justify the investment. And I think kudos to the Energy Commission for this code cycle, who really was able to let the market grow in this area that is critical for decarbonizing multifamily buildings. And we've got plenty of more of that to do in the next code cycle for commercial systems and others for heating in particular. And the thought on Christian's presentation, I think it would be really interesting to run more scenarios to look at, I think you mentioned that the typical installation types that, in the north of the country will more likely to be basement or actually indoors. And also different draw patterns, right? Because not everybody is drawing as much as the standard Building America's draw pattern. There's the California Energy Commission's draw pattern is actually significantly smaller, and we see people who have more like the small or medium draw patterns than the high one, and it'd be interesting to see the difference. And so that there's also people have agency in terms of how much water they use, and they could say, well, I'm a pretty careful water user, and this tank should be fine for me, even if I live in this space.
Right. Well, I will invite Christian to answer this question at the Zoom meeting, because I think we are at time now. So what I will ask people to do, for those interested, the Zoom link is available on the top right here. One thing I learned is they will ask you for a passcode. The passcode is also available right there under the link. So I'm going to be switching over to that meeting. I invite everyone else to as well. But thank you so much for each of our presenters. It was a wonderful presentation, a wonderful session, and I'm looking forward to continuing the conversation, and want to thank you again for the time and thoughtfulness of all of these presentations and timeliness. You guys were great and punctual and landed right on time. So thank you so much, and we'll look forward to seeing everybody in a minute.
Thank you, George.